Coming from the Foundation, and this project is some pilot work for the Great Foundation's project. So the initiation of walking in infants is a stage in their lives as babies where the foot goes from an organ that's used for reaching and grabbing at objects to an organ that's used for bearing weight. So once the baby starts coming to stand, they start loading. They start loading with up to body weight or supported weight, and then they start loading it dynamically when they start to initiate walking. And this loading is irregular and often not consistent. And then they begin to load more and more regularly as they become more and more confident walkers. So this is the phase that we're talking about really, is the point where they become independent walkers. So there is literature presenting plantar pressure data in independent walking. I've picked 4 papers that are quite representative of what exists out there. It's not exhaustive, but it's quite a good representation of what I want to talk to you about. Hopefully you can see. So the studies have quite good participant numbers for our kind of research. Some of them are longitudinal studies, and I've just picked out the subject numbers that reflect the relevant group, and some of them are cross-sectional studies. They define the stages of development as once the baby starts to walk without support or can take a certain number of steps. And the age range tends to be around a year. Some studies do select by age rather than developmental stage. And they tend to use obviously high resolution pressure platforms because of the smaller contact area that we see in adults. So these are the same papers. The environment that the data is collected in tends to be a standard gait lab environment, and sometimes the child will be encouraged with a toy to get to the end of the lab because they're obviously not as happy as adults to follow instruction. Some of the distances reported are approximately 3 meters, and walking speed is self-selected in all the studies that are reported. And then we see the exclusion of data in these studies tends to be if the child is done in a irregular pattern, the trial is excluded, or if the toddler has stopped and turned or stopped and not continued to move. This data has also been excluded in research as well. So if we go to the behavioural sciences literature, it tells us how babies walk in a more natural environment. So there's a PhD student called Whitney Cole in the US who collects a lot of free walking data, and she's collected data on infants who are independently walking. And this is an example trial from her data collection. So this is what this infant did in 10 minutes in their lab. And as you can see, this is not really reflected in those protocols I just described. Well, it's not at all, in fact, reflected. So just to kind of summarise some of her data, 75% basically of the steps taken, or the bouts of walking, which is like a section of walking, are less than 4 steps. So these trials where a child has walked 3 meters are really not reflecting what an infant will do in an environment that's trying to be a real life environment, which leads to the purpose of this work, is trying to collect this data, plantar pressure data, in a more natural environment. And this is part of a larger project which will be collecting this data longitudinally, which we started. Unfortunately, I hoped I could come here with 10 or 15 participants, and I have 4, which is we had to prioritise our longitudinal research. So I've been testing younger infants who are not independently walking, and also babies have busy diaries. They don't always turn up, and they get chicken pox and they don't come. So I apologise now that my data is more descriptive, but in the future we will be obviously capturing a much larger data set. So this is our lab environment. We have foam flooring, foam cushions, chairs for the parent to sit in with the infant, and then we have approximately, it's quite small, we have 4 meters square. We're quite limited in terms of what area we could take for privacy at uni. And we selected privacy over volume, so we've got quite a small office, and then we have our Nagol platform embedded in the floor, which is the XL platform, so it gives us quite a large area for the infants to be walking. And the protocol is that the infants arrive, we do various other tests with them, but for this phase, They're put into this area with their parents or grandparents who are to come, and they have 5 minutes of free play, which you can imagine doesn't always result in what we want, but they come in for 5 minutes, and for this data, we collected 30-second sections of plantar pressure data, and I'm going to be presenting data from 2 of those sections for each infant, which was selected at random. So that's an example of what we end up with, which is obviously not what you would normally expect to see if you collected from an adult. So we have to temporarily separate the trial so that we can select the steps, because obviously the infant has walked back over where they've been prior. So we do that. We manually select a step in the Novell software, and we end up with a collection of first steps for each infant. For this data, we used every step that was dynamic in the trial. And we also have to exclude all the trials that border the platform, because the data, it gives us a warning and the data isn't correct, but we collect it anyway. To help us with this process, we use a coding software, so like a performance analysis software in sports science. We code what the activities the baby is doing. It's a bit more elaborate than what I'm going to present here, where we basically say, is the baby moving? Is the baby on the mat? What type of task are they doing? Are they carrying an object? And we have far more of these, but these are the ones that are relevant for today. And this is what we coded for this particular study was, are they moving? Yes. Are they on the mat? Yes. Because we don't want any of the other data. And as long as they were walking and not supported by a parent or leaning on a toy or anything like that, then we included that data here in this case. So for the babies, we ended up with a range of steps from 19 to 35 steps for each individual, which obviously a lot of these are only the steps that are on the platform, and then the steps that we didn't exclude. So there are obviously a lot more steps in the trial, but that's what we ended up with this data. And then I've got there the proportion of steps that we perceived to be in a straight line. So when we were coding, we coded whether the steps were straight or whether they were turning as well, which I'll come back to in a bit. So our contact areas, I've presented every person's data and then a mean at the bottom. So our contact areas around 42 to 46 centimeters square, but the main point here is the range is large around those, and you can see the coefficient variations quite high, 6 to 10. We collected like a similar data set on an adult walking and ended up with less than 5 for this. So with the peak pressures, we have quite high ranges again. We have a peak pressure mean around 130 kPa, which is equivalent to what we see in the literature. But again, we have quite high ranges, like particularly participant 3, we had like a really high peak when she was moving in the lab. So just to try and demonstrate that some more, this is one example subject. This is her steps, the contact areas, and the peak pressures. And you can really see that the mean, if we took the mean value, we're losing a lot of information, a lot of the characteristics. So all the studies I presented give us the mean of each individual, and we're losing a lot of the data that we see here. This is the same numbers from the previous slide. So you can see the ranges are high. So to try and describe why we have this variability, we separated, as I said before, the straight line walking and the turning walking. We used the automated average profile in the Novell. We didn't end up with much difference in the variations. So in the static walking and in the turning walking, the variation within those sets was quite consistent. It's the same for both of the participants that I've taken. The straight line walking had slightly higher peak pressures, and the turning had slightly higher contact areas. But the variation within those was quite consistent. So if we take our mean data set, we do end up with similar numbers to the literature. You can see our work sat alongside 2 of the larger studies. Our mean peak pressure matches quite well the first cohort in the POSH study, and our contact areas match quite well the other study as well. But that, if we just mean that data, we're missing a lot of the variation. And despite our protocol having that variability in it, we really need to include this variability, because that's what the infant's real life walking is like. So the main point really is that the external validity of the environment is really important if we want to quantify the real world plantar pressure on that infant's feet. And then how we treat the data is going to be really important in future with how we're going to try and convey our results and how meaningful our results are. So with our future work, we'll be looking at, we're starting to bring younger infants in, and we're looking at tasks that they would normally do day to day. So this little girl's just learned to pull to stand. So she pulled to stand in our lab, so we have data of her pulling to stand, which is something that she does regularly. And then when she stops walking, we'll have data of her walking in a more natural environment, and then we can actually really quantify real life tasks and real life plantar pressures rather than straight line walking with a mean data set of many infants. And this is just our wider project team and some cute baby photos of them as well.
All right, thank you very much. I think let's open to discussion. Yes, please.
Great talk, and I was wondering how might you distinguish the cruisers from independent ambulators, or early walkers from more mature walkers, like 12 to 18 to 24 months?
Yeah, so for our longitudinal work, within this work, it was a pilot study. We just kind of recruited infants who just started walking, and it was self-reported, so it's not ideal, but it was a start. So for our longitudinal work, we're recruiting babies who are just starting to grab their feet. So we've selected milestones that are quite easily identifiable for parents. And then we're asking the parents to actually video, because parents video anyway, to show us a video of the first step, so that we've got an actual timestamp. But when they come into the lab, we'll have like a cruising time for, so the people who come in and visit too will be able to cruise, and we will collect cruising data on them. And that will probably be all they can do. So we would have like a static stand, and then we would have cruising. But then with the independent walkers, we'll attempt to remove any surface that they could cruise on that would be near the pressure platform. So we would only end up realistically with independent walking steps, or if the parent becomes involved for some reason, supported walking, which we can code with our coding, but we'll try and remove the coding and have everything automated instead with our motion capture. At the moment, we're using 2D video.
Thank you for a lovely presentation. I realise how challenging that must be. You're spending an incredible amount of time and effort to get this beautiful data. What do you want to do with it?
Good question. Yeah, I'm spending a lot of time. So the actual full data set, in terms of plantar pressure, we can look at how plantar pressure changes from like an earlier stage. So like the data that I've shown you is plantar pressure once people are mostly independently walking, and there is bits and pieces of supported walking. But if we can get plantar pressure from pulling to stand and from then supported walking cruising, it's a proper timeline of how plantar pressure changes, and therefore how the demand on the foot is changing, and maybe that's a proprioceptive influence or a change on foot skin. It's part of a much wider study that's collecting like musculoskeletal ultrasound, skin properties, motion capture with older children. So it's kind of about trying to quantify the influences of the foot as infants begin to weight bear, and then trying to maybe link those together. But we have like separate research questions for each of the phases really.
Thank you very much. Next speaker is from Auckland.
Good afternoon, everyone. I'm Chi Chang-mei from the Auckland New Institute in the University of Auckland. My topic today is foot shape, perceived comfort, and also the plantar pressure distribution during the long distance running. Let's come to my background. As widely accepted, running is one of the most accessible physical activities to improve fitness and also prevent obesity, cardiovascular disease, and also some other chronic health issues. And the prolonged running popularity increased greatly in recent years. And also in US, over the past 10 years, the full marathon finishers increased about 30%, and also the half marathon finishers increased about 300%. And the running events held in 2016 increased an 18% compared with 2015. And also in China, over 2.8 million participants of all the running events through the country in 2016. Foot is the primary interface between the human motor system and the external surroundings. And most people tend to wear shoes to do all kinds of physical activities. And footwear comfort has been proven to be linked with fatigue injuries and also performance. And the comfort is characterized by the foot-shoe interface physical characters like plantar and also the upper pressures, and also the impact of stability and foot shape. Often, the shoe fit is defined under static or just short-term dynamic situations. However, the foot shape varies greatly during long-distance running. And in this study, during long-distance running, the foot shape variations will lead to ill-fit discomfort. Thus, the blisters and also the cones come out, which will lead into abnormal compensatory movements. This might be a potential injury risk for the muscular injuries for the runners. And footwear technologies have developed greatly since 1970s, either for the purpose of injury, for the performance improvement and or injury prevention. Properties like cushioning, motion control, lightweight, minimalist shoes or barefoot shoes that come out. And it's widely known that extensive participation of activities will lead to the increased potential injuries. And however, the running injury rates have not changed greatly over the past 40 years, and there is no consensus explanation for the trend of running injuries. And Benedict believed that this is because the definition to the injuries and also the running population changed greatly over the past 40 years. Thus, in this study, we are aimed to investigate how the foot morphology changed and when discomfort occurred, and how plantar pressure is distributed over a single long-distance running event. There are 26 recreational male runners, short runners, participating in this study. They are all barefoot track, and they all prefer the shoe size of 41 euro. And they all have history of completing either full or half marathon. And they all had no foot deformations or other lower extremity disorders in the past 3 months of the test. And the shoes, as illustrated, the shoe is an EVA midsole and with a thickness of 25 millimeters to the heel region and a density of 0.2 gram per cubic centimeters. And the Young's module is 0.52 megapascal. And all the shoes were distributed to participants 1 week before the test to ask the participant to do the normal daily activities for adaptation and increase the flexibility of the shoes. A 3D foot scanner were used to record the foot shape data, and the insole, novel insole were used to measure the plantar pressure distribution, and 150 millimeter visual analog scale were used to record the perceived comfort, with the most left end as not comfortable at all, and the most right end as the most comfortable. And also the heel region midsole material property was measured with the impact tester pre and after the 20 kilometers running, following the American Society of Testing and Machine standard, with a total mass of 8.5 kilogram and height of 15 centimeters. And all participants were running on standard outdoor track, outdoor 400 track. All the tests were conducted immediate after 10 kilometers running and immediate after 20 kilometers running. All the tests were conducted in the indoor lab. The indoor lab is right beside the starting and ending lines of the track. As we found out, the forefoot width reduced greatly after 10 kilometers running, and the arch height dropped greatly after 20 kilometers running, and the forefoot girth reduced greatly after 20 kilometers running, and the foot volume shrinked consecutively from static to 10 kilometers and 20 kilometers running. Let's come to the perceived foot comfort. And perceived foot comfort scores in the heel region and also the forefoot region reduced greatly after 10 kilo and 20 kilometers running. And the overall comfort reduced greatly after 20 kilometers running compared with the static condition. On the contrary, the perceived scores of arch height and real foot and forefoot width increased greatly. For the shrinking foot volume, this might be the dehydration because all the participants run long distance in this study, and this will lead to more foot-shoe interface slip and friction, and thus the reduced overall comfort and forefoot discomfort occurs. And also for the increased forefoot width and arch height scores, this might because the shrinking forefoot volume, forefoot width, and also just lead to more variation in the forefoot. And because of the arch drop, lead to the perceived arch height score increase. For the heel rigid middle sole property, the energy return decreased greatly after 20 kilometers running, but the peak G value, also a property to illustrate the shock attenuation property, showed no significance in this study. For the peak pressure to the heel region and middle foot, also the second and third metatarsa and also the first metatarsa increased greatly after 20 kilometers running. On the contrary, the peak pressure to the big toe region reduced greatly after 20 kilometers running in this study. The peak pressure difference distribution changes in this study is show increased greatly in the medial foot part, that is middle foot, second and third metatarsa, and also the first metatarsa. It is inconsistent with previous studies of long distance running. For the increased peak pressure in the middle foot part is might because the arch drop, and for the increased peak pressure to the heel region, this one thing is because of the energy return of the shoes, and also all the participants in this study are real foot strap. This might lead to the increased peak pressure after long distance real foot strap running. And for the increased first metatarsa and second and third metatarsa peak pressure and decreased big toe peak pressures, this is because for the long distance running, the fatigue intrinsic foot muscles, which lead to the weakened toes, particularly the big toes dynamic gripping functions. Okay, let's come to the conclusion and implication parts. And the forefoot shape varies greatly during long distance running. And for recreational runners, also professional runners, thick and breathable cotton socks are advised to reduce discomfort because of the foot variations, and also to prevent the potential dermatological problems. For the newly constant running shoes, it will not degenerate the impact attenuating property in the heel region after a single long distance running event. And the toe is dynamic, especially the gripping and ambulatory functions among recreational runners should be enhanced to reduce forefoot loading for the prevention of potential metatarsal injuries. A future study will investigate the running on different surfaces like asphalt road, netted ground, and treadmill. Also, the lower limb joint kinematic and kinetics will record to reveal how the mechanic changes. And also, the foot muscle changes will be analyzed with MRI and also advanced study. Okay, thank you for your attention.
Thank you. The paper is open for discussion. I would have a question. Did you check for the temperatures of the skin?
Yeah, this is one indication of the
Because we realized in a similar study that when you run for 10K, the material might change as well. Or would that reflect your data? No, in general, we realized by heating the shoe up that the midsole materials would change. Would that also be reflected in your data? Yes. The properties would change a little bit. Would that be reflected in your data?
Because for this study, I only there's a paper I didn't basically this that for the pre and post the material property effects within the 12 hours before and after the we're going into the dependent test and
Any further questions from the audience? Yes, Julie?
Quick question. I'm intrigued with one of your first recommendations, which was that you're advising thick cotton socks. Could you please explain why that? I can understand the shape, but why cotton? Most people are actually advised not to wear cotton. So where does that come from?
Because in this study, we found out that the forefoot shrinked greatly after long distance running, and we defined that the shoe shape didn't change throughout the study, and because the foot shape changes, which will lead to more slip and friction inside the shoes. So as a compensation action, so we advise long distance runners to thick and also cotton is breathable, so for the noise and also the sweep to breathe this out.
I think you might get disagreement from some runners.
Thank you.
The next study is coming from Taipei, and it was IDC.
Good to see you again. My topic of this time is the effect of 4 medially repeated high heel shoes modification on foot pressure during standing or walking. So again, my name is Plantar Pressure from Untitled University in Taiwan. Women are usually wearing high heel shoes for pre-posture demonstration. However, the high heel shoes interrupt the natural foot position, resulting in discomfort and pain around toes and ball of the foot and heel and arch, and produce a chain reaction of negative effect up to lower extremities and the spine. Furthermore, the high heel shoes would displace the central pressure locus anterior medially during the stance phase of high heel gait, and lead to increase in confined pressure caused by high pressure distribution over the forefoot, and increase the hip foot as well, which may cause deformation of toes such as valgus and heel pain over a long period. So what if I give some modification in high heels? The modification would in turn allow more space for the metatarsal medial forefoot, and the pit as a resistance on the medial metatarsal head area would prevent the forward sliding of the foot during gait. So purpose of this study was to investigate the effect of the 4 medially repeated high heel shoes modification on foot pressure during standing and walking. 7 female workers were participating in this study. They are working in squat, and non-pitted and pitted high heel shoes were used for this study. Pitted high heel shoes, which means modified in this study, and both shoes were capitalized by 2 centimeter height forefoot outsole and 9 centimeter height heel with 1.5 centimeter spare heel base. And pitted high heel shoes has been molded with 1.5 centimeter radius and 0.2 depth around the first metatarsal head area, 4 medial part of the shoes, and using the 4 medially embossed the shoe length. visit the shoe last? I can remember it. Good. They gradually have that in the first metatarsal part. My photo is the movement. Subject were asked to perform the 15 minutes walking on the treadmill with random order of 2 types of shoes. And additionally 30 seconds of walking on treadmill and 10 seconds standing for foot pressure negative. As scan software was collected data of the distance from the point of peak contact pressure to the medial edge of the first metatarsal contact area and peak contact pressure of 4 foot of the metatarsal. The way to the distance of the PCB. Non-parametric Wilcoxon sign rank test and effect size were used for the statistics. And the BPCP was significantly increased in PD high issues during walking with large effect size. And also increased with medium effect size during standing. And on the area increased with large effect size in PD high issues during standing. So we found that wearing the PD high heel shoes resulted in the central shift of the peak contact pressure of 4 foot during standing and walking and alter the trajectory of central pressure. The tight-fitting toe box of high heel shoes can drastically stress the medial forward foot due to high pressure distribution on the first metatarsal head and big toe, which could lead to pain and deformation such as Howell's bug. So in our studies, the central pressure is moved or circuit to the more medial side instead of the first metatarsal, so it feels more comfortable. And then based on interviews from customers who bought these shoes, and they said it's more comfortable, especially walking push your face and they feel comfortable. So conclusion of the was the fitting the force metatarsal high shoes can reduce stress in the first metatarsal head and toe area during standing and walking. Thank you.
Questions? Yes.
Hi, nice talk, thank you. Tony, I'm from Stockholm, Sweden. If I saw it correctly, the pressure that was underneath the first metatarsal head appeared to, when the fitted shoes moved further medially, that really to the second metatarsal head. Do you think you might just be taking away one problem and causing a new problem? Do you think you'll be getting higher pressures underneath the second metatarsal heads if you remove it from the first metatarsal head and then maybe causing a problem in some new region on the foot?
The central pressure is moved more medially. Central pressure is more medially around second and third metatarsal head area. Then first metatarsal has less stress than before, and it also has more space around first metatarsal. Then they say it feels comfortable.
That's good.
Any more questions? So the next study is from Holland, and you know this guy?
Okay, so I'm not Jennifer Zwageling, who's in the program, but my name is Nico Bus, and I'm presenting part of her PhD work on the diabetic foot. And she couldn't be here because she's actually having a baby right this moment. So we all know the problem of diabetes, the global problem that it is, with 1 in every 12 persons in the world having diabetes, and the population of patients growing massively over the next 30 years. And 1 in every $9 spent on healthcare are on diabetes. Also, when it comes to the complication of the disease, it is a major problem. So 50% of patients will develop loss of protective sensation on their feet because of the presence of peripheral neuropathy. 19 to 34% of patients will develop a foot ulcer, which you see an example here on the top right. And a foot ulcer is a strong risk factor for infection and amputation, for the reduction of patient mobility and quality of life, and also for the increase in treatment costs, with a foot ulcer on average costing about 10,000 euros to treat. For that reason, I'm very happy with the recent review paper from 2 colleagues of mine and myself on this topic in the New England Journal of Medicine, which is addressing the problem of diabetic foot ulceration, and in particular on the problem of recurrence, because 40% of patients who heal from a foot ulcer have another foot ulcer within 1 year after healing, and 60% in 3 years. So with this paper, we really hope that the exposure and the attention to this problem increases. When it comes to prevention of recurrence, a lot of these patients are prescribed with custom-made footwear. And the primary aim of custom-made footwear when it concerns the plantar foot surface is to redistribute pressures from regions that are at high risk for developing a foot ulcer, like the hallux or the forefoot area, to other regions in the foot that are less at risk for developing a foot ulcer. And we know from the literature already how effective different shoe design interventions can be. So for example, the incorporation of a rocker outsole configuration, the incorporation of custom-made inserts, or the application of specific elements, pressure-relieving elements within the insert, where between 29 and 52% for the rocker outsole, custom-made insert showing 16 to 37% pressure relief, and these different elements 36 to 39% pressure relief. Another shoe design element that is often incorporated clinically in diabetic shoes is a carbon fiber plate reinforcement. Now this can be done underneath the insole, but often within diabetic footwear it's incorporated within the outsole of the shoe. And it's intended to reduce dorsiflexion of the toes by making the sole much more rigid, and therefore reducing pressure underneath the forefoot. But we have very limited data from the diabetic population whether this principle is actually applied. So the study aim here was to evaluate the effect of a carbon fiber plate in the shoe outsole on forefoot plantar deep pressures and patient satisfaction during walking in patients with diabetes who are at high risk of foot ulceration. The inclusion criteria were, of course, patients with diabetes who had loss of protective sensation because of peripheral neuropathy, had a high-risk foot, which meant that they had a previous ulcer or the presence of artery disease or foot deformity, and they were already habitual wearers of custom-made footwear. Exclusion criteria were an active ulcer, inability to walk, inability to fit in a semi-custom-made shoe, like we are testing, and also amputation of more than 2 toes. The diabetic shoe was tested that was an expert depth shoe that had a 1.8 centimeter thick and 18-degree rocker outsole in the forefoot part, and a diabetic custom-made insole was tested in the patients. So each patient was prescribed with such a shoe and such an insert, which is a pressure and shape-based insert within the shoe. We tested two outsole versions, one with a 3mm full-length carbon fiber plate in the shoe outsole, and one version of the shoe without such a carbon plate incorporated. We tested in-shoe plantar pressures using the Dark X system, had the patients walk first at their preferred walking speed and then standardize that for the other condition. We tested them for 12 mid-gait footsteps, and we randomized them for their condition, the order of testing. We tested patient satisfaction with a visual analog scale, using a score from 0 to 10, with 10 being the best perception, for walking comfort, shoe fit, shoe weight, and shoe appearance. So we tested 24 patients who were mainly male subjects, type 2 diabetic patients with an average age of about 66 years, high BMI, high degrees of neuropathy present, and exactly half of them had a history of foot ulceration, and also exactly half were habitual wearers of fully custom-made shoes, and the other half of semi-custom-made shoes. This shows the results on peak plantar pressure, and for the different toe regions, so the hallux and the second and third toe and the fourth and fifth toe, the differences were not significantly different, statistically significant between the two conditions. But for the metatarsal heads, the peak pressures were significantly lower in the condition with the carbon fiber plate incorporated compared to the condition that did not have the plate. Also, the midfoot was significantly lower pressures in the intervention condition. And for the heel, the peak pressures were significantly higher in the shoe condition with the carbon plate incorporated. We have indications from the literature that when you reduce the peak pressure under 200 kilopascals, that this level of pressure can be protected against the development of foot ulcer recurrence. And if you look at the percentage of cases where this below 200 kilopascal level was achieved, the percentages are quite high. So they are between 83 and 96% for the metatarsal head region, and also for the toe regions where foot ulcers often occur, they were 79 to 100%. So a lot of these cases were already considered optimal based on the reduction of absolute peak pressure. In terms of patient satisfaction, we found moderate scores for both the conditions, and there were no significant differences present between the conditions. So perceived walking comfort was very similar between the two conditions. Shoe fit was considered a little higher in the no plate condition. Also shoe weight and shoe appearance was relatively low in both conditions. So the carbon fiber plate shoe outsole significantly lowered the peak pressures at the metatarsal head with about 9 to 12%, which is quite comparable to single interventions, other single interventions that you can put into a shoe design for the diabetic patient. And midfoot pressures were significantly low with about 4%. Significantly higher heel pressures were found, but this is not considered a high-risk region in a diabetic foot, so we don't care too much about the higher pressures there. And the different aspects of lowering pressure at the metatarsal heads using this carbon fiber plate can add to the different components of other shoe design principles that eventually design the most optimal shoe for the diabetic foot. Close to 80% or more of the peak pressures were already below the 200 kilopascal level, so in absolute sense, we already achieved quite good footwear outcomes, and there was no significant effect of the plate on walking comfort and other perception elements. It may be potentially contraindicated for patients with a severe loss of proprioception, because clinical experience shows that patients with severe proprioceptive loss have some gait stability problems, and these shoes further decrease the proprioceptive feedback by limiting the joint movements in the foot. So there may be some potential contraindication for those patients. In conclusion, a carbon fiber plate in the shoe outsole is recommended when the aim is to relieve metatarsal head peak pressures in high-risk diabetic patients. And future research should assess the effect of a range of outsole stiffness on plantar peak pressure, walking comfort, and gait stability, so that we can try to achieve the most optimal solution for individual patients. Thank you for your attention.
The paper is open for discussion.
Would you mind defining the difference between semi-custom and custom-made?
Yes, with custom-made we mean that both the shoe and the insert is fully custom-made, whereas with semi-custom-made only the insert is custom-made, but it's incorporated in a standard diabetic extra depth shoe. So the shoe is not custom-made.
Thanks. Great talk. I was curious about the material properties of the carbon fiber element, because you could take this to the limit. You could put quarter-inch thick steel, 1040 steel in, it'd be very stiff, and you could put in memory foam. What do you think the optimal material properties would be to try to minimize pressure and really, more importantly, also recurrence?
Well, that's a very good question, and I think that's also what I recommended for future research, because these plates that were incorporated to increase the stiffness of the outsole used to be steel plates, but they increased the weight way too much, so these have become carbon fiber plates. And in terms of what is the optimal thickness and the optimal conditions, that's something that needs to be looked for. But these shoes, if you try to bend them, they are very rigid. So there's only about a 5-degree movement that you can actually put inside the shoe. But we need to find out what the most optimal situation is for individual patients. Yeah.
Thanks. What do you think? What is roughly the cost to apply those plates if you compare it to the costs of other shoe modifications? Because that's a very sensitive thing to bring it to a wide market if it's so effective.
Well, if you know in the beginning that you're going to put it in the very initial design, the cost will not be that high because you already incorporated it inside the shoe. If it's something that you're going to add based on high pressures measured, and then think, okay, would a plate be something to add to the footwear, then you'll have to take it apart and apply it to the shoe. So that would be a much more labor-intensive procedure. And then, of course, having a range of other opportunities to lower pressures, of which I showed a couple, that you can easily do within the workshop. For example, modifying the insert of the shoe would probably be a more cost-effective procedure. But if you know from pressure measurements and high-risk regions in the foot where how high the pressures are and how much you want to lower them, you can actually put it in the very initial design of the shoe, and that would not give a lot of extra cost.
Yeah, as Untitled Chapter as well. You mentioned about the pressure, but we know that the ulcer, right? Ulcer development is not only caused by the pressure, but also the rolling as well as the shear. So that's my first question. And my second question is, how do you control the 24 subset? Because they have the different categories of the diabetes, right? So some, even though they can walk 100 years or they don't have any pain or something, can we really assume that they are controlled group?
Well, they're representative for the group of patients who would you prescribe this kind of footwear to. So we looked, as I showed in the patient characteristics, for a wide range of patients who are habitual wearers of this kind of footwear. So they're known to having this kind of footwear based on the problem that they have. And therefore I think it's a very representative group. And in terms of the shear, yeah, that's the limitation of having the pressure measurements to date, is that we don't know about the shear. There are ways of trying to reduce shear based on more of an experience. For example, building up the shoe so actually you decrease the forward movement of the foot, but we cannot measure it. So these results are limited to vertical pressures and not shear pressures. But that's always a limitation of doing this kind of research. Yeah.
The next paper is from Chengdu, China, and it's dealing with obese plantar pressures in obese children.
Good afternoon, ladies and gentlemen. Let's introduce myself first. My name is Yan Xiang. I'm from China, Sichuan University. Today, my topic is the effect of food type on the food morphology and the plantar pressure distribution of these children. Okay, let's move to the first part. Let's look at the relationship between flat food and body mass. Numerous studies have acknowledged that with increasing the body mass, the proportion of children with flat food increased. And we can see that flat food presents a high incidence in obese children. And we can draw a conclusion here. Obese children with flat food tolerate not only the excessive load, but also the food structure deformity. And the purpose of this study was to investigate the effects of the food type on the food morphology and dynamic plantar pressure distribution of obese children. And we should answer the question, are obese children with flat food at a high risk for food deformity and food injuries? We select the participants from the database of 280 likely boys and 271 girls aged between 7 to 16 years. And the experimental group was 30 obese children with flat foot, and another 30 obese children with normal arch foot, which are matched to their counterpart for body mass, gender, and weight, are selected as the control group. Here is the descriptive data of the participants. We use input three-dimensional scanning system to scan the three-dimensional food morphology of the obese children in the half body weight condition. And we use the foot scan plant system to collect the data of plantar pressure distribution during walking, and use the footprint plate to collect the footprints. And we use the CS index and foot angle to classify the foot types into normal arch foot, normal arch foot, high arch foot, and lower arch foot. And totally 10 foot morphology measures were selected to calculate in Delcom PowerSheet software. And you can see the dimension here. And the plantar region was divided into 10 plantar regions. And 5 foot pressure parameters was selected to do the analysis, including peak pressure, foot time integral, pressure time integral, load rate, and contact area. And independent t-test was used to perform the statistical analysis. Here's the result. And from the result of the foot morphology, we can see the obese children with flat foot displayed significantly lower end-stage height and lateral height. And with the foot measures was normalized to the foot length, and we can see that obese children with flat foot displayed significant lower end-stage height and the longer end-stage circumference. And this is the result of the plantar pressure distribution. And we can see that obese children with flat foot displayed significant greater pressure, peak pressure finished the second to fifth toes ranging, and greater pressure rate and the larger contact areas finished the mid-foot region. And here is the result of the pressure time integral and the force time integral. We can see that obese children with flat foot decreased decrease, pressure time increase, and food time increase is fixed metastasis. From the results, we can see that foot dimensions increase and height should be considered into shoe last design. Small variations in foot morphology must be considered into the shoe last design to match the foot shape of children with black foot to the specific shoe to protect the foot from deformity. And obese children with black foot could be at an increased risk for mid-foot injuries and a lower risk of lateral metatarsal stress fractures. And thank you.
Thank you. The paper is open for discussion. Yes, please.
Ray Browning from NECI. Nice presentation. Do you have any data on the onset of obesity, and how it might affect these measures? So how long the children had been obese? It's a quite a wide range of participants from 7 to 16. Any idea on how long in their lives they had been overweight or obese as children?
Sorry, I didn't.
Repeat the question, please.
So just how long the children had been overweight or obese? So, how many years had they?
We did the research 3 years ago, and we found that they are obese since they are very little, for almost several years.
Thank you for your presentation. Do you know whether the flat feet were structural? Had the bony structures collapsed? Or did they have a thicker fat pad? So what is causing the flat feet?
Yes. We did a follow-up study last week, and there is interesting finding that some of these children, they are flat 3 years ago, but it's disappeared during the research last week.
Thank you very much. The next paper is coming from Korea and from Busan, and Dr. Park is giving.
Thank you for introducing. My presentation title is Analysis of Plantar Pressure during Climbing for the Development of Sports Climbing Shoe. Sports climbing is a very extreme sport, and so there are a lot of equipment also used. And so today we focused this in the middle of various climbing equipment as a sport climbing shoe. Climbing shoe is the most important equipment for sport climbing because they are enhanced for rock climbing ability of the climbers. So, we started previous stuff, and so we focused a lot of research papers, and we checked some point, and so and there is a lot of injury, and the narrative is during time. So also we interviewed this top level Korean female climber player, and usually she wears size 9 or 6, but during climbing she wears size 3 or 4. And so this is research purpose is that we analyze for plantar pressure in prototype designed with the different outsole hardness and structure. Yeah, 9 climbers we participated for this research. At first we checked this climbers shoes last, and then so we modify, and secondly we also developed for climbers last. And so we checked this climbing shoes last for this product. Yeah, you can see and there are hardness different. We applied a multi-layer design, so different color and also indicate the different levels of hardness. So we are focused and interviewed these clients. They used and wear the same hardness as climbers' shoes. So, but some of very high level and players, they request for the different hardness. So, in front of and behind this, we are thinking about how can I change the hardness. So, in the middle of outsole, we checked and we focused the hardnesses we separate. And so, edge of the palm and heel areas, we used the show A75 hardness. And then for the center of the foot and heel, we used the show A55. So for the control climbing shoe, just the same hardness, show A63. This control climbing shoe is very popular in Korean and also intermediate climbers. Yeah, we used the feather access system, and this equipment are very useful and for the every sport activity and experiment. A lot of people support. At the time is also we used the different system, but in here we just introduced preparation. And we also separated and masked in the M1, M2, M3, M4. And M1 is right lateral foot, M2 is right medial foot, M3 is right middle foot, M4 is right middle foot. So, major areas we checked the 3 different plantar pressure. First is contact area, second is maximum force, 3 is maximum mean pressure. This is experimental procedure. It is very difficult to experiment because walking and running is just for the surface very regular, but this rug is irregular, and also during action and some subject is very difficult to operation to participate. So we interested to climb with the following 4 climbing position. First is inside the step. Second is rock forward. So this counterbalance goes outside the step. We discussed this national climbing place teams. How can I recheck and action is defined? This is just a very short experiment scene. Maybe you can understand how is this experiment is going. Yeah, each subject will randomly assign the shoe, the mean of 3 measurements were used for all data. Yeah. Contact areas, especially in the row of M1 to C4, M4 we tracked, and so prototype A is, especially in the M4, is quite different. We checked, and the maximum force is also M1, M2, M3 variables we checked. Versus finally, maximum mean pressure is just M2, M3. Yeah. And then, in conclusion, we check this pitch curve balance in the upright position as maintained by using the entire foot to widen the base of support. So, also we use the biomechanical algorithms designed for this shoes also. In conclusion, this new sports climbing shoes is called Type A. It's a high gravity outsole, has a different level of hardness in the center of the forefoot and here and the edge of the forefoot and here. Also, this new sports climbing shoes was more effective than Type B. It's just the same hardness in reducing the maximum force and pressure based on superior contact area, which may be localized versus surface during climbing. So for the study, we will check the 3 motion analysis and another kinematic data. Thank you.
For discussion. So I have a question. So what would be the purpose of measuring the pressure? Would it be dependent on the traction as well? Do you want to have a shoe that is has a lot of flexion? So what would be advisable for such a shoe? What would be the value of the pressure measurements?
Yeah, I'm not sure about this. In the middle of this experiment is, this endpoint is we focused because during this climbing, as mostly of player they used the tool, but this at the same time, leopard is also important because toe and rear, especially hin areas, also hit the rock area, and so there is needed comfort area. So the core part and the rear part is at the same time we have to use the high hardness, and then center is more the comfortable hardness to be used.
Further question? Thank you.
Yeah, thank you.
To acknowledge the funders for this research. So they were Chopin Top Elm Footwear, who are a work footwear specialist company, and the UK government Innovate UK, and it was part of a knowledge transfer partnership. So, up to half of the working population are estimated to undergo periods of prolonged standing. So prolonged standing is generally defined as spending more than 50% of your time at work on your feet. And it includes professions such as those in healthcare, factory work, retail work, and food service, to name a few. So the problem with standing for prolonged periods of time is that it's associated with a very high risk of musculoskeletal disorders. So for example, the risk of low back pain has been shown to increase up to 1.9-fold, and the risk of lower extremity and foot pain has been shown to increase up to 1.7-fold. So there are multiple elements that impact the foot-ground interface when standing at work. So when we think about it, we have the foot, there's often an insole which is placed inside a shoe, and in a work setting there's often a form of matting or anti-fatigue mat used, and this is placed directly onto the flooring itself. So previous research has primarily focused on the use of softer matting and anti-fatigue mat in the workplace, and it's consistently found a decreased subjective discomfort during prolonged standing with the use of these mattings. So footwear and insoles have been less widely investigated, despite the fact that they are easily portable and easy to individualise as well. However, we do know from previous research they have the ability to influence comfort. However, what we don't know is the impact of the individual footwear parameters on the body over prolonged periods of time. So therefore, the purpose of this study was to investigate the impact of prolonged standing on the body and to determine the effects of altering the footwear density. So how did we do this? So 12 participants were recruited for this study with an even mix of male and female. Each participant attended 2 sessions set at least 24 hours apart. And 2 pairs of surgical type gloves were tested, as seen in the picture here. Now these were deemed by the manufacturer to be appropriately different in manual feel or hardness, so as to be able to constitute 2 different products from their point of view. The footwear were geometrically identical as they came from the same moulds. And the entire footwear was made of EVA as well. So at each session, participants stood for 3 hours. They completed continuous tasks at a desk at a set height of 0.9 meters. And these tasks were created to replicate the movements made in the work environment. So they required standing and shuffling, but they were not permitted to walk or move away from the desk at any point. So data was collected at the start and every 30 minutes thereafter, giving us 7 data collection points. So following variables were collected for a minute at each data point. So the 3D kinematic data, force plate and plantar pressure data. So the plantar pressure data was studied in the areas as seen in the picture here. So the heel, the medial lateral midfoot, the metatarsal regions and the hallux in the toe. Calf circumference was also measured as this was related to blood pooling that occurs in the lower limb. And subjective comfort was assessed using a 100mm visual analog scale for a variety of measures, so such as that seen at the bottom here. So moving on to results then, and first of all I'm just going to focus on the effects of time, and then we're going to move on to look at the differences between the footwear. So looking at the subjective data then, on the left here we have all the different parameters that we assessed. So this included shoe sole hardness, whole body discomfort and fatigue, low back discomfort, and a range of lower limb variables as well. And what we see, the arrows indicate any point at which a significant increase occurred over time. So what we see is every single one of these variables increase over the 3 hours of standing. But perhaps more importantly, all these variables significantly increase within just 90 minutes of standing. So we saw a similar increase in calf circumference over time, as seen here, and this was a significant at 60, 90 and 180 minutes. So this suggests that blood pooling is occurring in the lower limb during this period of standing. Moving on to plantar pressure then. So here we have the contact area and the pressure time interval data, and again the arrow indicates when the significant increase is occurring over time. I've chosen the 3 main areas that changed with time to present here. So if we look, the very first increase we see is in the heel, and this increase occurs at 30 to 60 minutes. After that, between about 60 and 90 minutes, we start to see increases in the pressure variables in the lateral midfoot area. And then by 120 to 150 minutes, we see increases in the medial midfoot area. So actually what we see is the plantar pressure changes are occurring faster in areas of higher pressure. So for example, the greatest pressure seen in the heel corresponds to the fastest change in the plantar pressures. What we also see is the centre of pressure was shifted laterally due to greater pressure increases on the lateral side as opposed to the medial. We get a corresponding increase in the internal ankle inversion moment, and therefore we actually see no changes in the ankle joint angles because of this. So moving on now to the differences between the footwear. So here is a table of the mechanical data from the showing the differences in the materials of the footwear. So what we see is about a 10% difference in the hardness and up to a 20% difference in the shock absorption measures. So all this testing was done externally in the lab. However, it's worth noting that both of these shoes do have a low Shore value in comparison to a lot of shoes that are commercially available. So the only subjective variable that differed between the footwear was the lower back discomfort. So over time we can see in both the softer shoe, so I'm showing the red line, and the harder shoe in the black line, lower back discomfort increased over time. However, this was significantly greater in the harder shoe. So it's also worth noting here how large the standard deviations are, and this was due to individual differences between both the footwear they were wearing, as well as due to their differences in changes that occurred over time. Okay, so moving on to the plantar pressure change then. So going back to the three variables that we discussed before, that's changed over time, and here we are looking at the pressure time integral. And what we see is that the changes that occur over time are actually exacerbated in the softer shoe. And this is significantly so for the heel and the lateral midfoot. However, although the changes in the plantar pressure variables for the softer shoe were greater, this did not translate to differences in the